Okay, good afternoon everyone. Hope you all had a great lunch and didn't eat too many sweets so that you stay awake in this talk. So I've always wanted to visit Berlin, and I'm really happy to be here and have this opportunity to visit the city and be at this conference. I'm Nick Pentreath, and today we'll be talking about how to take your Spark ML pipelines to production using the portable format for analytics. So a little bit about me, ML Nick on Twitter and GitHub. I'm a principal engineer at IBM, and there I work for the Center for Open Source Data and AI Technologies, or CODE. Previously, this team was known as the Spark Technology Center, and I've been there for a couple of years working on Apache Spark, machine learning, AI, deep learning. And more recently, the team has expanded its mandate to focus on anything that's related to the combination of open source, data science, and AI tech. So very exciting for us. And this is just the beginning of the new team, so watch this space. I'm an Apache Spark committer and PMC member and wrote a book, Machine Learning with Spark, a little bit out of date now, but if you're interested in that, you can go and find it online. And I talk at various conferences and meetups around AI, machine learning, and a lot about productionizing machine learning and how to actually use these models in production, which is what we'll cover today. So we'll start by talking a little bit about the machine learning workflow, and in particular the deployment phase of that workflow and the challenges that are related to that. Introduce the portable format for analytics, an open standard for deploying analytic applications and machine learning models. And then talk about PFA for Spark ML pipelines and exporting those to that format. And finally, look at performance comparisons and the future directions of PFA on Spark. So, as we all know, machine learning is simple, right? You take data, apply machine learning, profit. Easy. But in reality, that machine learning workflow is significantly more complex, right? So the workflow spans processes and teams. You have the data, which is sitting around. Some of it is in data storage systems, SQL systems, no SQL. Some of it is streaming, arriving in real time. It's in different data silos, even across organizations. You need to take all of, and that is the domain of your data engineers. They're managing this data. You then need to ingest it into the machine learning pipeline and the workflow. And this is the domain of your data scientists, researchers, and so on. You're ingesting it from these different data sources using various formats, various frameworks into this pipeline. And once you're there, you've got a bunch of raw data. You can't just throw that into a machine learning model. Okay, you can't just apply your latest deep learning to that necessarily. So you need a data exploration phase, data visualization. Is there missing data? What does the distribution of this data look like? Trying to find outliers. How do I handle all of this kind of thing? And then feature transformation and engineering. So taking that raw data, processing it into a kind of more refined form that is then in the right format for feeding into your machine learning model. And in addition to that, engineering new features from that data. So combining them in different ways, combining data sources, and enriching that data. And then we get to what is traditionally viewed as the data scientist workflow or the machine learning job, which is model training and evaluation and selection. But in reality, as we all know, that takes up a very small proportion of your time. But this is the exciting bit. This is where you get to throw all the different models at the data and the problem, try to pick which one is going to perform the best. This is where you get to use your latest and greatest gradient boosting model or deep learning model. So great, now you've done this whole phase and you go through this process a couple of times and you've got a model, but what do you do with it, right? You need to deploy it. And it's not just about deploying that machine learning model, which takes in some feature vector and spits out a prediction. You have to deploy that entire pipeline that comes before, right? Because the raw data that you have to predict on is not a feature vector. It's in that format that the data was in the beginning. So any new data coming into your predictive pipeline in real time, you need to apply those same transformation steps. So that entire pipeline needs to be deployed. So now you have that, assuming you can solve this problem easily, You have that in a live system, and you now need to monitor it, evaluate that model, see if it, if there's a sort of concept drift or the distribution of the data is changing over time, your model is degrading. So you need all this evaluation in real time. Perhaps you're doing A/B testing, banded algorithms to play different models off against each other or optimize them, and so on. And then finally, the workflow actually becomes a loop because the model itself and the predictive system itself is having an impact on the data, particularly in personalization recommendation systems, ad targeting, these kind of domains. By making predictions, you're actually influencing the future data, training data that you're generating. So you need this feedback loop to bring back what was the prediction, what was the outcome into this workflow, and that goes back into the data and ingest system. So this is a very complex workflow, and in fact loop. It spans these different teams, your machine learning production engineers, data scientists, data engineers. And it also spans tools. So each of these personas and each of these phases require different tool sets and prefer different tool sets. We'll talk about this machine learning or data scientist sub-workflow, which is data ingest through to model training through to deployment of the final model. So you have a plethora of different data formats. CSV, yes, I mean, that's probably a large proportion of the data sitting out there is in this zero schema, no metadata, bunch of CSV files. You might have some more structured data sets, Parquet, average, JSON. It might be sitting in HDFS, etc. You have to deal with these disparate schemas if they even exist, and they're changing over time. So new data columns, features, fields are being added all the time, deleted, made redundant, and so on. In the data processing feature transformation stage, pipelines are becoming critical. So you can't, as I mentioned, you can't just deploy the model. It has to be the full pipeline of data pre-processing and transformation that comes before that. So toolkits like scikit-learn pipelines, various ones in R, Spark, TensorFlow, Transform, TF Transform for TensorFlow, have this concept of a pipeline with different stages and different transformations. And then model training, each toolkit has its own version of cross-validation, train validation splits, hyperparameter optimization, being able to plug and play different models into that. So all of these need to be supported by different teams and even within the same team. Some data scientists might have more of a stats background. They might prefer R. Some might be more into deep learning, maybe using Python. Some might even be using Scala, and so on. And then once you've got that final model, the pipeline and schemas need to be consistent between training and prediction. There's no point in deploying this model and then you have a kind of concept drift or a skew between the training and test data where you're transforming things at test time or prediction time in a different way. You're just going to get garbage in, garbage out in that case. And all of this is a really small but critical piece of the overall puzzle. So this is taken by the Google paper, Hidden Technical Debt in Machine Learning Systems, or Machine Learning, the High Interest Credit Card of Technical Debt. And I really like this image because it really puts it into perspective. Without the ML code, that little black box in the middle, none of these systems would work, and we wouldn't have cutting-edge machine translation and image recognition and ad targeting systems. But they really are a 5% or 10%, if that, of the overall system. So they need to talk to all kinds of other systems. And in particular, on the deployment side of things, this serving infrastructure and monitoring and some of the analysis that goes on in your deployed model is critical. If you just throw out a script there that has been written in a Jupyter notebook, how does it interact with the serving infrastructure? How does it get monitored in a standardized way? How does it do logging? All of these kind of things. So I've mentioned some of the challenges, but the data science workflow, and in particular the deployment of models, needs to bridge these gaps. So you have friction between teams. You have the data scientists and researchers. They want to use the latest and greatest. They might be on a bleeding edge version. They might even be training TensorFlow models on a release candidate or off the master branch on GitHub because they need the latest feature. Production does not like that, right? Production engineers like stability and do not like to be woken up at 2 o'clock in the morning with pager duty, calling them, telling them that the system is on fire. So they want to minimize changes and have tight control of the runtime. And they don't like new things quite as much. They also care about performance. Again, you don't want to have Black Friday or Cyber Monday type of traffic coming through and everything falls over because a new model was deployed that runs on R, for example, and just can't keep up, or Python or whatever the case may be. So the data scientists will use Python, R, Jupyter Notebooks, sometimes Scala if they're using Spark. The production engineers probably prefer things like Java, C, C++, maybe Go. So you have this, this disparity between the frameworks, the languages, and the kind of business needs, what they care about. And at the end of the day, business itself might care a little bit about the fact that you're using the latest, greatest deep learning models, so that they can use that in their marketing. But actually, all they care about is that at the end of the day, the product performs, it does what it says, the business impact is there, the metrics are there, and they always want it to be working and on. Again, if your predictive system, for ad targeting or recommendations is failing, the business doesn't care whether it was deployed on Kubernetes, right? It's not working. So across all these frameworks, I sort of mentioned it a bit earlier, the performance characteristics can vary widely. So this is, the production team would like stability and performance. Ideally, they would like one system, one runtime, where they can understand it really well, manage the dependencies, manage the performance, and have certainty that any new model pushed into that system is going to have a reasonably predictable performance characteristic. But this is not the case. In some cases, Python might be really fast because it's calling into NumPy, it's calling into optimized TensorFlow libraries, it's using GPU. In some cases, Python might be horrendously slow. So you're then dependent on whoever wrote that script for model deployment. So on the subject of deployment, this is not deployment necessarily in the DevOps sense. So model deployment means obviously taking that pipeline and kind of publishing it or getting it out there and using it. Deployment in the DevOps sense is a similar concept. You take a piece of code and you put it somewhere. But most people would say, well, yes, just use Docker. Use Kubernetes, have a container that wraps up your model and pushes it out there. It's true that takes care of the DevOps side of that deployment, but it doesn't necessarily address these concerns of dependencies, versioning, performance, because if you wrap up that R script in a Docker container, yes, it makes it easy to deploy it onto your cluster, but it doesn't give you that certainty about performance. It doesn't necessarily give you a standardized framework for exporting metrics or for calling into that model as a REST API. So containers are useful but incomplete solutions. They're definitely part of the solution for deployment, depending on what framework you end up using. But this lack of standardization is really the key here, and that ends up leading to custom solutions. So packaging up everything with custom scripts and doing a lot of manual work to make sure that there might be some overall standard for, let's say, how to expose a model as a REST API, but it's not baked into the software. And using containers also puts a lot more of the DevOps burden onto your data science team. So in some ways that's good because they take ownership, but you need a lot of that process to be automated, packaging things up into containers, for example. And that is a lot of work and a lot of maintenance burden. Finally, where standards do exist, some of them are out there, and we'll talk a little bit about one shortly. They are not complete enough, or they have issues that cause all the benefits of standardization to be lost because you end up writing custom extensions and, again, customizing things to make it work for your use case. So there's no point in having a standard if you end up customizing something. So those are the challenges in general deployment. And what about Spark? Well, Spark in particular has all these challenges, though it solves some of them through its sort of cross-language support. But it has more which are sort of quite critical in this case. So the first is that in order to serve Spark models. And by model, in this case, I refer to a trained Spark ML pipeline. So that might be one logistic regression model. In most cases, it is the entire pipeline of feature transformations through to a machine learning model. And in order to deploy that or use it, you have to use Spark. So you need to, even if it's running a local instance of Spark, you need to score that model using Spark. And this is because Spark ML pipelines depend on Spark data frames. So this is a fantastic abstraction for dealing with tabular data. And the Spark ML pipeline setup of having feature transformers and models that operate on data frames, transforming one data frame into another as you go, that's a great abstraction for training. And it would be a great abstraction for prediction time, except for the fact that, again, you need the data frames. That means you need Spark. And data frames are built on top of the Spark SQL engine, which means you need to create a data frame, even if you are predicting on a single row. You need to do query planning and optimization for every single request. And you need to do task scheduling, even if that is purely on local multi-threaded. So all of this introduces significant overhead. And performance-wise, as we'll see, you're talking about of the order of seconds in terms of latency. Now, for some applications, obviously batch scoring and some near real-time streaming scenarios, that might be acceptable. But for the vast majority of real-time scoring situations, fraud detection, ad targeting, recommendations, many, many use cases, that is not acceptable. You need a few hundred milliseconds latency at the most. And the world of ad targeting, that drops to a few milliseconds latency. So scoring with Spark is problematic. So what you want to do is you want to take that trained Spark model and you want to publish it outside of Spark. Well, that is pretty much impossible to do out the box. There's limited support for some standards like PMML, which we'll talk about. But effectively, you need a custom solution all the way through. You need to have a writer and reader for Spark's custom format, which is a combination of Parquet and JSON. You need to write your own custom format. You need to typically write a translation layer, which will take that model, put it into your own machine learning library. And you either need to write your own machine learning library for scoring, or, as some have done, Netflix has actually done this, for example. Or you need to somehow do a translation between Spark and turn it into H2O or scikit-learn or something else. So how do we solve this problem? Well, one way is to use an open standard and use a model interchange format. And PMML, which is the predictive model markup language, is one such existing standard, probably arguably the only viable open standard in use today. And that was created by the data mining group, of which IBM is a founding member. So PMML is an XML-based serialization format and defines common machine learning operators and some data transformation operators. So it allows you to export your machine learning model and your analytic application to this format and then load it up into a PMML engine and away you go. But there are many limitations to PMML. Anything that is supported by PMML works really well. But if your particular use case, operator, transformer is not quite supported, then either it's impossible and you hit a brick wall, or you go and you customize PMML with custom extensions. Now, the minute you do that, the standard is no longer a standard, right? It's just you started from that standard and you created something of your own. So if it's completely custom, it's not portable across languages, runtimes, and so on. So PFA, Portable Format for Analytics, is the data mining group's answer to PMML. PMML version 2, you can think of it. So it's slightly different. It's a JSON serialization format. It uses Avro schemas to specify the data types. So all the data types, inputs, outputs, whatever function, data types functions take is all specified by Avro, which gives you virtually complete flexibility when it comes to types. Where it differs from PMML is that it doesn't just encode a pre-specified set of model operators, but it has actually effectively a mini functional math language and type system or schema specification. So there are various built-in operators and functions, and you can combine those in a functional manner, taking the input from one function as the output the output of one function is the input to the next, and in that way create a pipeline of functional transformations. And the built-in kind of functions and operators and schemas are the ones that you would typically find in machine learning pipelines. So support for arrays, maps, linear algebra, and so on. So because of the type system and the functional nature of PFA, once you create what is called a PFA document, which is the serialized form of your model, that PFA document contains all the information needed to score that model. So that is the input and output types and the exact mathematical transformations that happen on the input data to create the output. So because of that, if you load it up into a compliant PFA engine, a reference implementation, it can be statically verified at runtime. So you know exactly that that is a valid PFA document, that you can execute it, and that all the types match up. So this really gives you true portability across languages, frameworks, runtimes, versions, and it decouples the model producer from the model consumer. So the producer can then become any version, any fancy deep learning framework, whatever the case may be. The consumer doesn't actually care. It just cares that you give it valid PFA. So what does this look like in practice? This is a simple example with logistic regression, multi-class. And here we see some of the elements that I mentioned about PFA. So this is a subset of the entire document, which specifies the model. And we have the input and output types, which are specified as Avro schema. So in this case, the input is just a double array, so a dense vector. The output is a class prediction, an index. And what's important here is we have the action. So the action is the set of transformations or the set of functions applied to the input to create the output. So in this case, the JSON is not really, it's slightly human readable, but it's a little bit tricky. But of course, JSON is really here for the purposes of using machines and computers to manipulate it. So we can still see how it works if we read it kind of backwards. So we take the input and we apply this built-in model.reg.linear function, which is linear regression. And that is really a wrapper around a simple vector.product plus a bias. So standard issue linear model. And you'll notice that there's a cell model there, reference, and we'll talk about that in a little bit. We then, the output of that particular function will itself be an array, and we just do a soft max and an argmax, and we've got our prediction. So it's very naturally maps to the kind of mathematical understanding of what this model will be doing, that prediction. So I mentioned that cell reference. So one of the arguments to the linear regression function is a cell. And our cell in PFA is a way of managing state. It's effectively a global variable. And each invocation of that PFA document, which is the calling of that kind of action function, effectively at the beginning of each invocation, the cell state is immutable. So it's set to whatever it was at the beginning. So it's a way of storing typically things such as model coefficients, mappings from terms to indices for vocabulary. These kind of little pieces of state that your machine learning model or transformer will require. Again, the types are specified as Avro schemas, so you can pretty much put whatever you want into a cell. But in most cases, it's going to be fairly simple stuff like arrays, mappings, and so on. So you can see that the type is a record. That's an Avro record, which is kind of like a little struct with fields. And it has one field, which is the vocabulary. And the vocabulary is just a map. So in Avro, the map always has string keys, and the values are integers. So this maps terms in a vocabulary to indices in a feature vector. And this is the kind of thing that you would have in a kind of count vectorizer type transformer that will take a piece of text and turn it into a bag of words vector. So in the previous example, the model cell would be defined in this set of cells, and that model cell has two components, which is the coefficient vector or matrix and the bias. So given those two pieces of information, the linear regression function can compute the dot product between those two input and the coefficients plus the bias. There's also something in PFA called pools, which is really the same as a cell, but it's persistent. So you can think of it as a database table, or field in a database table. So actually updating that during the action will update it for all users of that piece of data. So it's not that commonly used, but it can be used to maintain some kind of global running count, for example. So some other features of PFA, it really does try to be a mini language. So it has conditionals, branching structures, loops. You can create and maintain local variables, and there's local scoping within functions. It has this comprehensive built-in function library, so you can do array manipulation, maps, strings, linear algebra, and math. And you can combine any of those functions into a user-defined function. So that can either be a lambda, so you can actually define it in line as you would in Python using lambda functions, or in Scala using closures, or you can define it in a special field in the PFA a document which is for user-defined functions, and that can be called in your action. It has some built-in help for common models, particularly trees. So it's certainly possible to just do it in raw PFA, but it becomes very verbose. So they just provide some helper functions there to do some of the common things, like find the nearest point cluster in a clustering model, walk a decision tree model, or a set of decision tree models for an ensemble, compute a linear model, and so on. Some very basic exception handling, logging. That's actually one area that could definitely be improved. It sort of works, but it's not that helpful in real life. So PFA is the successor to PMML. It tries to be a better open standard for serializing and scoring machine learning models, analytic applications. And it works very well. What it lacks at the moment is a way to easily create PFA documents in kind of the JVM land. So there's a reference implementation on the JVM for scoring, and for that scoring engine. And there, in Python and R, there are some DSLs and helper functions for creating documents. And they've used these to create, export for various R models like the GLM libraries and clustering and so on. And the same could be done in Python to create export for scikit-learn, for example. But in JVM Scala land, there's nothing. So this is what our team set out to create. And it's called Aardvark. I'm from South Africa, and an Aardvark, if you don't know, is literally an earth pig in Afrikaans. If any of you are Dutch, you'll sort of maybe understand it. But it's an anteater. It's a pig that walks around and eats termites. So Aardvark is our PFA export engine for Spark. So Aardvark Core is a Scala DSL for creating PFA documents, and you can see it on the right there. And it's pretty much just some Scala code that creates a bunch of expressions that get exported as JSON, and we can use a library like Avro4S to make our lives easier when creating data structures. So that allows you to easily export and automatically export case classes to Avro schemas. And then Aardvark Spark ML uses this DSL to export Spark ML pipelines to PFA. So this is actually the Aardvark equivalent of what we saw earlier. So we have an input, we have a cell which we define as linear model data. And now that dense linear model data is just a Scala case class with a constant or bias and a coefficient. And we don't have to define how that gets exported to Avro or JSON, how we put that into the PFA document. Avro4S does that for us, so nice and easy. And we wrap up the action with the built-in functions, and we pass it the input in the model cell, and then we create a little PFA document. And again, we use Avro4S to make our lives easy. We don't have to go and define Avro schemas manually, which is not terrible, but not that fun. We can just pass in some Scala types there as tags, and it'll do the magic for us. So in terms of the status of Aardvark right now, It can export most Spark ML components as of 2.3. There are a few missing features, but most of the predictors, in other words, almost all the machine learning models, with the exception of some of the more advanced clustering models and some of the recommendation models, are supported. Most feature transformers, not all of them. There are no particular roadblocks, barring one or two. It's just a question of time to actually get them done. And pipeline support in a initial form. So pipelines are fully supported, and as long as your pipeline is made up of components that can, have support in Aardvark to export to PFA, then we can merge them together into a PFA pipeline. And along with that, tests. So testing that the PFA that is generated from a Spark model, when scored, gives exactly the same results as Spark to make sure that there are no mistakes. So the basics of exporting a Spark ML component to PFA are fairly straightforward, but there's a couple of challenges. One of them is that a Spark ML model actually has no knowledge about the schema. So it takes in a data frame and spits out a data frame, and all the code sits there to do the transformation and check schemas, but the model itself cannot, it doesn't have any kind of knowledge of that. There's no type system around the model that will allow you to automatically extract that. So it means that you have to do a few clunky things like take in the input data frame as well as the transformer or pipeline into Aardvark, examine the schema of that data frame, extract all the fields, and then construct a kind of a row or an AVRA record that encapsulates all of the fields at the beginning of the transformation and carries them through. So very similar to the way Spark itself does things. It takes an input data frame and appends a column, more or less, or a few columns with each transformation. We had to do something similar in Aardvark. But it becomes a little bit clunky, and it would be really nice if a Spark ML model was this kind of statically typed thing that knew exactly what its input and output types was, because then you could just inspect that and away you go. So the approach for doing pipeline support is verbose and potentially not the most efficient, but it works. One of the more important missing features in PFA is that there's no support for generic vectors, so dense or sparse generic vectors, and in Spark, you can have a data frame vector column that has dense or sparse, and all the models can work on each. So at the moment, there's not much of a workaround. We're just working on dense vectors just to get things out the door. But that is something that needs to be addressed. And it's possible, in raw PFA, but it becomes very verbose and complex because you need to, do a lot of checking. Is it an array? Is it a dense array, sparse array? And then you have to have a different code path for each and every function that accepts one of those arrays. So this should be really baked into the PFA standard. There's no reason that it can't be. Okay, so briefly on similar projects, I mentioned PMML. PMML, has its shortcomings, but it works. It works really well. And perhaps surprisingly, given that it has these shortcomings, there's a JPMML-Spark ML project, which covers a lot of Spark ML components, definitely worth taking a look at. The licensing there may or may not be a problem for you. It's AGPL, but it's worth looking at. There's some PMML support added to Spark, or being added to Spark right now, and that's the link to the Jira issue, so watch that. MLeap is a Scala project created by CombustML, focused on model serving. It offers very complete Spark ML support, and it is an open format, but it's not a standard. So everything's written in Scala, and they've got their own format. So it works, but it's much less generic in my view than PFA. So it has a speed advantage and a coverage advantage, but it does produce this tight coupling between producer and consumer. So you have to, in deployment, you may have to actually run multiple versions of MLeap to score multiple versions of Spark, or MLeap itself will become more and more complex because it has to handle the differences between different versions of Spark, or TensorFlow, or sklearn, or whatever it's using. So I think that is actually one of the main downsides. And then briefly, the ONNX, or Open Neural Network Exchange, that's being championed by Facebook and Microsoft. Very similar to PFA in that it defines a computation graph, effectively, of the operators that you apply to the data transformations. But but it's more focused on deep learning and tensors at the moment. So for sort of traditional machine learning, it's not really usable. But definitely they are looking at it, so watch this space. So we did a quick test of comparing a sort of prototypical pipeline of categorical feature indexing, vector assembling numerical columns together, and a linear regression model, and compared Spark MLeap PFA. So as I said, the Spark time is something like 1.9 seconds a record in this example, so it's not even on the graph. And as you can see, PFA is about still 3 times slower than MLeap, but they're both within an order of magnitude, and PFA is just over 1 millisecond, MLeap sort of 0.3 milliseconds. So this points to some work that needs to be done in the PFA reference scoring engines, but I think the gap can be closed. But in any case, if you compare both of them to Spark, there really is no comparison. You can't use Spark for real-time scoring, but you certainly can use these two. Okay, so in summary, PFA provides an open standard for serializing analytic applications and machine learning models, true portability across frameworks, languages, runtimes, teams, systems, and a true decoupling of the model producer and the model consumer. This is solving, we believe, one of the most significant, if not the most significant, pain points in Spark ML and actually using Spark ML in production. But there are risks. PFA is a young standard. It needs to still gain adoption. I've indicated the performance issues that might be there and need improvement. And a standard can move quite slowly because it's governed by committee, not unlike open source projects, I guess, in some ways. So fixes, enhancements, and changing that standard is not always so easy. So in future, Aardvark is not open source yet. We're working on that within IBM. It'll take, there's a process to go through, and nothing can be guaranteed, but I'm hopeful that will happen soon. We will initially be focused on full support for Spark ML pipelines, and then look at PFA export for scikit-learn and popular Python libraries, because many R models actually do exist already in the Hadrian project, and you can go to the link and check that out. If anyone is interested in actually working on adding more support, that'd be great. We would like to propose a few improvements to PFA, generic vector support, and a couple of other things to make it a little bit less cumbersome. And then finally, look at the options around PFA for deep learning. At the moment, it doesn't support generic tensors, GPU, all of the things that would be required, the various operators. But in many respects, it's more flexible than something like ONNX and other standards that might be out there for deep learning. So there's this, if the standard can move ahead with better GPU and deep learning operator support, there's no reason that PFA can actually could not be used as the standard for exporting deep learning models. Yeah, so thank you for your time. And there's a bunch of links and references. I'll publish the slides online or on Twitter. I'm not sure if DataWorks will be publishing slides, but either way, you'll get them. Thank you. I think we might have time for 1 or 2 questions.
Is there a timeline for open source release?
Okay, the question was, is there a timeline for open source release? I can't give you a firm timeline. It's something that has to go through an internal process at IBM, but I'm hopeful that it won't be too long. So I can't commit, but I would like to push it as much as possible in the next couple of months.
For a project already using one of the other projects you talked about, so PMML, MLeap, ONNX, how would you estimate the complexity of switching to PFA?
Okay, so the question was around if a project is already using, let's say, PMML or MLeap, what is the complexity, or should you even, I guess, switch to PFA? Well, the short answer is at the moment, it depends what the project is. So if it's Spark, well, Aardvark is not released yet, so I wouldn't advise switching to PFA just yet. If it's R or Python, well, you would be able to create your own export of your Python models and your sklearn, so it's certainly feasible. If you are already working with PMML, translating PMML to PFA should not be too tricky. And in fact, there's some work around automating that process, because PMML is a subset of PFA. So any PMML document is definitely translatable to PFA. It's just automating that if you have a lot of PMML sitting around. So there's some work by the Open Data Group, and if you follow the link to Hadrian, that's their GitHub, and you can find Open Data Group. There's some work around that, automating the translation of a PMML document to PFA. I'm not sure how well it works. I think it kind of works, but it may not work for everything. So I think PMML and PFA can coexist side by side, and I would advise on investigating PFA and probably starting the process of, where possible, using a tool to translate those across, and shifting new work to PFA, for example. But there's complexity there. You need to run both engines. But the nice thing is, if you have, let's say, a Java server, you can plug in a PFA engine, the Hadrian engine, and you can have your JPMML or whatever other evaluator you're using. And they can both run concurrently together, and so you can support both in one engine. So I think the complexity there can be managed. For MLeap, right now MLeap is a great project, and it's performant, and the coverage for Spark is there. So switching there would be a slightly more challenging, but it really depends on how much custom stuff you have. So if it's all just Spark ML, built in, then as soon as Aardvark supports it, well, switching is just switching your export writer to use PFA and spinning up a new scoring engine. But it's not as simple as that, because obviously everyone has to do their own performance testing and look at the dependencies, the complexities, and test things out. So yeah, no short answer to that. I think the MLeap versus PFA discussion or decision is partly about performance, but partly about whatever your views are about the future of each standard or format. MLeap is managed by a small startup company. Not to say that's good or bad, but there are risks involved in that, right? That need to be evaluated. PFA has its own upsides and downsides. For me, the biggest thing is, I believe an open standard, whether it's PFA or PMML, really does break that coupling between producer and consumer. It does give you the portability and the flexibility. It reduces complexity, in terms of managing versions, managing dependencies, managing frameworks, managing custom code. To me, that is worth a switch. But of course, your mileage may vary. Any other questions?
Yeah, the scikit-learn support, not everything's supported at the moment, is that right? In terms of models?
For PFA or for
PFA?
at the moment, nothing. No. So the focus of our work around Aardvark was Scala and obviously Spark. The nice thing about Spark is that once you solve the Scala side, obviously the Python and R APIs are just wrappers, so you automatically get support for those languages. So that would be a kind of V-next piece of work. So once we get the Spark side sorted out, we'd look at something like sklearn. But in the same way that sklearn pipelines, if you look at each individual transformer, Spark ML and sklearn are quite close in what they're actually doing and the concept, because Spark ML borrows a lot from sklearn in its design and even in deciding what to export, what to create. So I think it would be relatively straightforward once we get there. Cool. I think we're out of time. So thanks very much, everyone.